Hello everyone, I'm Dr. Fabien Payusson, and in this presentation we are going to talk about Buffon's needles. And the goal here is to see the crossing between empirical and formal mathematics. So without any further ado, we are going to start the presentation. Hello everyone, so today we are going to do a bit of empirical math. So what do I call empirical mathematics? Well, to do what I call empirical math, we are going to need a pen here, and here we are at my house, and luckily I've got laminated floor and I've got regular spacing between the wooden planks. Now I'm going to use, for example, this pen, and the actual experiment I'm going to do is simply do something like this and drop it on the floor. Now, what I need to do at that stage is simply record with a 0 if there is no crossing of this particular line, or a 1 if basically it crosses that line. So in this particular case, this is crossing the line, and therefore I can say that this is a number 1 I should put on this. Now, in principle, what we need to do is to actually repeat this experiment something like at least 1,000 times, and take the ratio, or at least do something with the ratio of the number of times we get to 1 and the total number of times we actually dropped the actual pen. Now, what I do in this particular instance is that it turns out these are my kids' colored pen, and I've got more of them. So I've got a bunch of them like this. So what you could do is essentially do the same. So you, instead of doing, one experiment, let's say 20 times or whatnot, you take 20 pens and then you drop them like this. Usually it's much more fun. And then actually you need to care to count these intersections. So for example, here we've got 1, and then here we've got a second one, the red, and then so 3, then 4, then we've got here, we've got a 5 with the blue one. And there is a special rule, which is that there is obviously in my floor, there are edges, right? And the only pens that I can look at are actually the bulk pens. So that's the one that are not touching any edges. So I'm removing from my initial batch the number of pens that are essentially touching the edges, because they have been influenced by the edges. So if I count the number of intersections, and I record the number of crossings, and then I also count the number of bulk pens, color pens, then I can record basically and do things much faster. So instead of 1,000 experiments, maybe I just need to do about 100 or 200, depending on the number of pens you start from. So that's the experiment which I'm going to run, and I'm going to show, the outcome of that experiment if I repeat it many, many times. Right, so let's summarize a little bit what this experiment is about. So we first need to drop pens or needles, whatever you have at your disposal. This can be toothpicks, this can be chopsticks, whatever, of a given length L. For this experiment to work, and what is coming to come as well to work, you need the length of these needles or pens or whatever you use to be smaller than the spacing between the lines that you are looking like about the crossing. And so the spacing here is called D. So the length of the needles or pens is L, and the spacing between the lines on the floor or on a tabletop experiment that you would have to be D. Now, once we have got this, then we drop them and we count the number of crossings between the pens and the lines on the floor. And we take care of counting only the ones that are not touching the edges for the whole calculations that is coming in a minute. And then we repeat many times this experiment, and we try to do something with the data. I'm going in fact to show you just in a moment what we do with it. So here is at the bottom is a small portion of the data I've got, and I'm just going to go through some of these columns to tell you what they represent. So here on the left hand side, this is going to be the number of bulk pens. So these are the ones that are not touching the edges when I've dropped the pens on the floor. And so in particular, this number 14 is going to be fed into the total number of pens that essentially were in the bulk and crossing or not crossing with some lines that are on the floor. And so this variable is called n bulk. Now, likewise, we've got the number of intersections. So that's the number of intersections between pens and the lines. And so this number here is going to be n intersect. Now again, this number of intersections is amongst the pens that are not touching the edges. And finally, we've got this particular part here, which is a normalized inverse frequency. So what the hell does that mean? Well, this is a quite maybe cumbersome looking formula, which I'm going to call x, and which is 2 times L over D, so the ratio of the length of the pen divided by the spacing between the lines on the floor. And then this is multiplied by the ratio of the total number of bulk pens that have been dropped on the floor over the number of pens that are intersecting with the lines, and again the number of pens amongst the bulk ones. Now in this particular instance, this is a trial number 1, therefore I've only dropped the pens once, and so I got this particular number, and here I get basically the ratio 14/6 here. Now in case you want to redo this experiment or rework out the particular formula I'm using, the L for me is 15.6 centimeters and D is equal to 19 centimeters. Okay, just in case you want to retrieve some of these numbers by yourself. Now, of course, if you do it at home later on, and I'm going to encourage you to do so, then of course L and D are going to be different. Now, let's have a look at what happens when we move to, let's say, do the experiment a second time. So this is going to change the total number of bulk pens that we can discuss. So this is going to be 14 plus 17. And the number of intersection that I can count is therefore the sum of the number of intersections that have been observed in each of the experiments. So the first one and the second one. So it's 6 plus 8. And in the end, the variable x is going to be 2 times L over D times 14 plus 17 over 6 plus 8. So I hope now that this is relatively clear how this is going to work. And now what I want to do is essentially show you the data that I've collected in my Excel file, and then what is the kind of value I got for x as I continue doing the experiment over and over again. Right, so here we finished with 130 repetitions of the experiment. Now it actually takes a bit of time to do this 130 times, but this is, or maybe this is worth it. So here we obtain in the end this particular number for x, so 3.14 and then 5991236. By the way, here I'm simply just getting out the number given by Excel. Of course, you would also do something maybe more carefully using significant digits and so on. For the time being, I just stick with this particular outcome. Now, this formula, the formula that gets into it is basically x, 2 times again L over D, and then times the sum of all the total number of bulk pens, so again pens that are not touching the edges once they are on the floor, and then over the number of observed crossings between pens, between one of these pens and the lines. Now in total here it means that we've got 130 terms to be added together, and then the ratio of these kind of additions. So this is a number we obtain. Let's keep this in a corner of our heads and then move on to a different way to approach the problem. And this different way is what I call a formal mathematics perspective. So what is formal mathematics here? Well, essentially the goal is to propose a mathematical model that somehow is going to represent the real experiment that I've made in my living room. Okay, so you can think of it as a game where you've got some objects which are mathematical objects, and you are going to need to describe the space that can be explored by these objects, and then you are going to introduce whatever other quantities and objects that you need in order to model the particular things that you recorded or that you extracted from the data. So in this particular instance, the part of the mathematical objects that we want to look at is basically here I've drawn 2 lines. Obviously here I need to draw at least 2 lines to show the spacing d between the lines, and in blue I've got something representing a needle. Now of course this could be a pen or anything else that simply looks like a stick. Now this is of length L, and again the spacing between the red lines is actually d. Now what we can look at here is the space that can be explored by this particular needle or pen in this characterization, and in particular it shouldn't be redundant, so we try to look at the smallest amount of configuration space, which is not something that is going to be a repetition of something else. So let's look at how this may look like. So here we notice that if I draw a dotted line just in the middle, at the, let's say, midline in between the 2 red lines, I've got essentially a distance d over 2 between the dotted line or the dashed line and the red line. Okay, so there is some form of symmetry between the 2. If the needle is within the gray area or within the white area, essentially the 2 are going to be equivalent. So what I can look at here is focus myself on the gray area that I've put here. Now when it comes to the position of the needle, of course I can characterize the position of the needle simply by looking at its center, or any other point, to be honest, would work for the position itself, except that, as we are going to see in a moment, rotation of the needle is possible too. So because rotation usually occurs about the center of the object you're looking at, center of mass, then it's more sensible to take the center here to characterize the position of the needle. Now, in this particular instance, essentially the needle can move anywhere in this gray region. The x direction, if you will, is not going to matter much. So the horizontal direction here is not going to matter much because it does not influence crossing of the red line. So we are not going to care about it. The y direction, however, which I'm going to mention or call altitude in some of the coming slides matters, right? Because it tells us essentially where there is possibility to cross with the red line. So once we have this, then we can say that the value y for the position of the needle, so again that's the center of the needle, can take any value between 0 and d over 2 if I set the origin of the y-axis to be in the dashed line. Alright, so that's for the first manner to express one of the, if you will, degrees of freedom of this particular needle. Now coming back just here for clarity, I'm coming back at the center here, and one of the things that can happen obviously is that the needle or pen can rotate, and as it rotates then you can measure the corresponding angle theta between the horizontal line and one of the ends of your pen. So that's kind of it. And in this particular instance, you see that the angle theta, again, not to be redundant, is going to be between 0 and pi. Now, one way we can then formalize this graphically is by representing the space or set of all possible configurations graphically, and that's what I'm doing here. And essentially, this is every single point in this beige rectangle. So you see on the y-axis you've got it goes from 0 to d over 2, so this is the interval we mentioned earlier, and likewise for the theta axis then it goes from 0 to pi. So once we have this, then we can try to create the new object, and that's the final one that we are going to need, which has to do with a subset of the configuration space. So this is here I've got a subset I, y of the interval 0 d over 2, and I've got a subset I theta of the interval 0 pi, and the Cartesian product between the two gives you the subset of all these things, where every single point in that red rectangle corresponds to some configuration of your needle. Now what I want to look at here is a probability that I call P for a given for the needle to be in the configuration, in one of the configurations in that set, okay, in that rectangle, red rectangle set. So the thing is that probability of a set for being in a particular set is an object, is a mathematical object. And in fact, that's a mathematical object which we are going to be interested in this particular formal mathematics perspective. Now, as in, let's say, video games, once you have an object, you actually need to have rules on how this object is going to behave, and essentially, the rules that characterize that object. When it comes to probabilities, they are characterized, classically at least, by what are called the Kolmogorov axioms of probability. Now, it turns out that although this sounds kind of fancy, and maybe it is, there are only 3 of them. And essentially here I'm going to refer to them as rules. So the rule number 1 is that probability, here's the probability of this subset, the right rectangle, has to be a real number between 0 and 1. So that's the first rule. The second rule is that the probability for the needle to be in any one of the possible configuration, so that's the probability of the entire beige rectangle, is necessarily equal to 1, right? Because a needle cannot be in an impossible or non-existing configuration. It has to be in either one of these configurations. And finally, the third rule involves a second set, which is not overlapping with the first one, and here that I'm taking as being the Cartesian product of an interval I y prime and I theta prime, and that I draw in blue. And the third rule says that the probability for the needle configuration to belong either to the red set or to the blue one is equal to the sum of the probability for the needle configuration to belong to the red set plus the probability for the needle configuration to belong to the blue set. And that's it. This is basically here laid in a not even half a page. This is like the whole of probability theory. Now, once we have this, what we can do is try to provide a model. As you can see, from these particular rules, there is nothing we can calculate. So we need to provide a probability model in order to, for example, use rule number 3 to try to figure out some new probabilities and so on. So the model we are going to use here is a so-called uniform probability model. What it says is that under these equally likely outcomes, we've got that it's as if we were sampling a point at random in this rectangle, so that the probability to sample one point is the same as to sample any other point in that rectangle. So there is no region of that rectangle which is favored compared to another one. Now, mathematically, the way to write this down is as follows. If you take a subset of this beige rectangle, so again the red rectangle here, then it says that the probability of that red rectangle, or at least for the configuration to belong to that red rectangle, is equal to a constant c times the area of that rectangle. So you see, it's incredibly convenient because we can relate probabilities to geometric quantities like areas, volumes, etc. Now, the important bit here is that the constant c is independent on the subset I choose. So if I had chosen the blue subset from earlier, the constant c would have been the same. We are going to see that this is going to be important later on. So that's a probability model that we are going to use. And what we want to find out now is, because we need to relate it to the empirical mathematics experiment we've done earlier, which has to do with crossing of pens with lines. So what we want to find out here is that if I've got my needle here with an angle theta, and somehow I fix this angle theta, I want to find out what is the configuration that is going to lead to a crossing. So if theta is fixed, the only free variable I can change is essentially y. So I'm going to leave this up. I put a bit more than the first possible crossing just so that it's kind of visible to you, but in principle I should have stopped as soon as the needle touched the actual red line. Now I'm going to call this particular altitude where the first instance of crossing occurs y min, and this is a function of theta. Okay, so this is going to depend on obviously the value of theta, and any y value above that y min is going to lead to a further intersection of the needle with the line, okay, with the red line. So that's really great. Here we've got a way to quantify for now this thing, which is if y is larger than y min, then this is going to work out. Okay, so once we have this, we can try to write out the equation for y min. So again, remember, y min is the value of y such that the tip of the needle is touching for the first time the actual red line. So the equation for it is y min is equal to d over 2 minus L over 2 sine theta. Okay, one way to look at this is basically to tell you that the y coordinate of the black spot here is on the one hand d over 2, because it's on the red line, so it's obviously d over 2, but it can also be written as y mean plus L over 2 sine theta, by definition of y mean. So now what we get in the end is that because any y larger than y mean is going to be a crossing configuration, then for any value of theta, I can simply plot the region that's in yellow, the region which is corresponding to a crossing configuration. So in practice, because I want to know the probability for a crossing to occur, then it means that I need to know the probability P of this area in yellow. Okay, so the probability again for one of the needle configuration to belong to that yellow area. Now remember what we had said earlier, that the probability for this is going to be a constant times the area of that yellow domain. But what is interesting as well is that the probability for basically the configuration to be any of the possible configurations is also equal to C, so the same constant times the area for times the area of the beige rectangle. Now what we can do from there is simply take the ratio between these two equations, and you can see that we are getting rid of the C's, so that's really nice. So we are getting here that the ratio of the probability for the configuration to be in the yellow area, which is about crossing configuration, over the probability for basically anything to occur, any of the possible outcomes to occur, is equal to the ratio of the corresponding areas. But that's where this becomes a smart trick, because if you remember, when we looked at the Kolmogorov axioms, the axiom number 2 states that the probability of this beige rectangle is equal to 1. So in the end, we get that the probability for a configuration to be in this yellow domain is equal to the ratio of the corresponding areas, so its area over the area of the beige rectangle. So we are almost there, but we need somehow to find a way to calculate the area of this yellow domain. So the way I'm going to do it here is as follows. I'm going to say that the area of the beige rectangle is of course equal to the area of the yellow domain plus the area of its negative part. So if you will, the complementary part of the yellow domain that is going to form the beige rectangle when put together. So if I do that, I can actually get, when I replace in the above equation, that the probability for being in the yellow domain is 1 minus the area, the ratio of the area for being in the complementary domain, beige domain, over the total area of the beige rectangle. Now the difficult part here could be if you do not know how to calculate the area under a curve. So I remind you that we actually know the equation for the curve that is drawn in red here. This is simply y mean, so this is essentially y is equal to d over 2 minus L over 2 sine theta. Now the way to calculate this, if you have seen this or not yet, is related to what is called the fundamental theorem of calculus. And it says that the area of this region is the integral from 0 to pi of d over 2 minus L over 2 sine theta d theta. Okay, now whether you know how to do this or not, if you want me to give some details of it, I would be happy to do it during the questions, but I'm simply going to give you the outcome of this right now. This is a quite simple integral to evaluate. And you would find something like this. So this is d times pi over 2 minus L. Now substituting back before substituting anything, I need to calculate the area of the rectangle. And luckily a rectangle area is quite easy to evaluate. This is simply the width times the length. And so this is d over 2 and then times pi, and we're done. So then we can substitute back into the above equation, and we get that this is 1 minus, and then there is parenthesis, 1 minus 2L over pi d. Putting all of this then back together, we get that this is the probability for a needle configuration to be in the crossing configuration is therefore 2L over pi d. Okay, and that's the main result we can get within formal mathematics perspective, so some kind of game with rules and some ways of modeling the pen and the crossing condition. So let's summarize a bit what we have seen so far. So we've got on the one hand the empirical mathematics part, where we performed a bunch of experiments and we recorded them and evaluated the following quantity, which is 2 times L over D times n bulk over n intersection, and we obtained after 130 experiments the value 3.1459912336. Okay. Again, here I'm not using any significant digit thing, so there would be something to be said on top of it here. Now, in formal mathematics, we have looked at something a bit more abstract. We have looked at a quantity called the probability, and we have looked at the probability for a needle expressed as an infinitely thin object with very sharp kind of boundaries and so on of a certain length, L, and what are the chances for it to actually cross, given that all possible configurations are equally likely. Okay, so that's a very important kind of consideration. So here we found that the probability for a crossing to occur given this kind of equally likely thing, which I'm calling here a uniform, is 2L over pi d. I can put it in a form similar to what we have on the left by saying that we could get actually pi, the number pi, as being 2 times L over D times 1 over P crossing, given this uniform assumption. Now, the pi is a number in formal mathematics, and this number is actually defined in very different manners that enable people to obtain essentially formal estimates and exact estimates of the digits of pi. And in particular, if we stop at the 9th decimal, these are the exact digits for pi. So this is 3.141592653. So we see here that with the two different things we've done, we actually got on the left, in fact, something that looks like an estimate of pi, which is actually in agreement with what we've got on the right, up to the two first decimals. Now we see that, of course, what we were doing, in a sense, is not necessarily estimating pi. Obviously, that was kind of the idea. But the bridge is not in terms of pi. The bridge between the empirical and formal mathematics is basically in these two middle formulas. It's basically telling us that we can, in fact, infer from this at least approximate agreement between the two sides, between the empirical and formal mathematics, we can suggest that the ratio of the number of intersection of the number of pens that have been put on the floor without touching the edges is approximately the same as the probability for a crossing to occur under the assumption that all outcomes are equally likely. And that's the interesting bit. That's how you basically make the connection between something which is due to empirical mathematics and something on the right-hand side which is purely formal and in some sense coming outside of a game. Now this particular let's say experiment was proposed by Georges-Louis Leclerc de Buffon in 1733, and this is this gentleman. Well, he was much younger when he proposed it. He was, I think, about like in his 20s. And the thing is that he actually proposed it because he directly postulated this particular connection that a way to evaluate this formal quantity, which is a probability, under the uniform hypothesis would actually be to simply do some experiment in real life. And his objective was in fact to propose an experiment that you could do in real life to get various estimates of pi through essentially random operations. So in case you would want to see a bit further, that's kind of the first time people were suggesting some what is so-called Monte Carlo experiments in real life in order to estimate some kind of abstract number, which is here pi, which, as you may know, has infinitely many digits with no repeating sequences. Right, so this is basically the end of this presentation. I hope this would have inspired you to maybe try out this particular experiment. Maybe you would get a better precision than the one I got, or a better agreement with some of the digits of pi than the one I got. And maybe this enabled you as well to observe that there is different ways of looking at mathematics. And we've got, on the one hand, experiments that are done in some sense in the real world, and then we've got some formal, very well-defined things, and then we need to find a way to match them together, or at least to say that they are approximately going to be equal to each other. So on this, I leave you, and if you've got any questions, I would be happy to answer them.